Welcome to the CSEC Physics May 2024 Paper 2 Solutions video. Let's get into it. Question 1. Identify the types of lenses shown in Figure 1. So, lens A, that is a concave or diverging lens. Lens B, that is a convex or converging lens. Part B of question 1. A student used the apparatus shown in Figure 2 to determine the focal length of a lens. She adjusted the position of the lens and screen to obtain a sharp image on the screen. She measured the image distance V, deduced the magnification M of the object, and recorded her results in Table 1 below. The Table 1 has row headings V in centimeters that go 20, 30, 40, up to 80, and M, which is the magnification, which has no units, and those values are stated as well. If we were to draw a graph of these values using a scale of 2 centimeters to represent 0.50 on the y-axis, what would it look like using the grid provided on page 7 for 8 marks? So, the grid provided in the exam paper already comes with the title at the bottom, so all we need to do is to make sure we label our axes. So our horizontal axis, that will be the image distance V in centimeters. The vertical axis will be the magnification M, again, that has no units. Then we need to pick a suitable scale. For the horizontal axis, 2 centimeters to represent 10 centimeters would be suitable. And on the vertical, we were told to use 2 centimeters to represent 0.5. So that means that we'll number starting from 0, and then we skip 1, number 10, skip, then 20, skip 30, and so on and so forth until we reach all the way to 80. And then similarly on the vertical axis, we start at 0, skip 1 and 0.5, then 1.0, 1.5, 2.0, and so on and so forth, all the way up to 4.2. That's all we'll need. Then we'll plot our values. So when CSEC grades, you get 1 point for every 2 marks that are plotted accurately. So here we have 7 points that need to be accurately plotted. So that will be 1, 2, 3, 4 marks. Then we need to draw our line of best fit. That will be the final and the 8th mark. Our line of best fit should go through as many of the points as possible. If 1 or 2 aren't on the line, that is fine. There are always experimental errors. Then, part 2, we are to calculate the gradient G for 6 marks. So, remember that gradient is rise over run, or y2 minus y1 over x2 minus x1. So, whenever you find the gradient for the Physics CSEC, you get a mark for drawing your dotted triangle. Remember that the dotted triangle should not be points that are on your line of best fit that were plotted, but any other points on your line of best fit. So here we can pick these points that you see being outlined with our red dotted line. The lower left hand corner has coordinates of 30, 0.75, and the upper right hand corner has coordinates of 75, 3.25. So substituting into our equation for the gradient is going to be 3.25 minus 0.75 divided by 75 centimeters minus 30 centimeters. So that's going to be 2.5 divided by 45 centimeters, which will be 0.056 per centimeter to 2 significant figures. Part 3 says, given that G is equal to 1 over F, calculate the focal length of the lens F for 3 marks. So for 3 marks, first thing you should do is to rearrange that formula to make F the subject, because the focal length F is what we want to find. So rearranging G equals 1 over F, we would have that F is equals to 1 over G. The second mark is for simply substituting. So we'll have 1 divided by 0.056 per centimeter. And then finally, we'll get 18 centimeters rounded off to 2 significant figures. Part C of question 1 says, Figure 4 shows a full-scale diagram of an object O, which has a height of 3 centimeters. The object is placed 8 centimeters in front of a diverging lens L. Part 1 of Part C, given that the focal length of the lens is 5 centimeters, Draw the ray diagram in figure 4 to find the image of the object for 4 marks. So, since we know that the focal length of the lens is 5 centimeters, then we can put our capital F at 5 centimeters from the optical center. Then we need to draw our rays. So the first and easiest ray that we can draw is the one that goes through the optical center, because that is going to be a straight line, because any ray that passes through the optical center is always undeviated. Then next, I'm going to draw a line that is parallel to the principal axis, and when it reaches the lens, it's going to refract away from the principal axis, and it refracts in such a way that it appears to come from the principal focus capital F. When I retrace those lines back to the principal focus, I should use dotted lines, because we use dotted lines for virtual light rays. And then finally, the actual image of the object, I have my vertical arrow to represent the object at that point. Then part 2 of part C says to record the image distance. From my scale drawing, I see that that is approximately 3 centimeters. Part 3 of part C says to state whether the image is real or virtual. Well, it's going to be a virtual image. How do we know? Well, it's because that light ray that we use with the dotted lines, that means it's a virtual image. Besides that, you could also know that it's going to be a virtual image because diverging lenses only produce virtual images. And that's it for question 1. Question 2. Figure 5 shows a bottle filled with water resting on the ground in 3 different positions, A, B, and C. We're to state the type of equilibrium for each of the following. Position A, that will be unstable equilibrium because it is easily toppled over. Position B is stable equilibrium because it is not so easily toppled over. A has a smaller surface area, B has a larger, not surface area, but I meant to say base, and then position C, that is in a neutral state of equilibrium, because if you try to topple it over, it will not really topple, but it will just roll around on the ground wherever it is. And another key thing to note is that for option C, position C, the center of gravity, if you were to push it, right, push that bottle, it would neither be lowered or raised. It will just roll around at the same level. Part B, define the term moment of a force and state its SI unit. So we could say that the moment of a force is the product of a force and its perpendicular distance from the pivot to the line of action of the force. The SI unit is the Newton meter. Part C, figure 6 shows a uniform meter rule balanced horizontally on a fulcrum with a mass of 0.24 kilograms hanging from one end. G is equal to 10 newtons per kilogram. Part 1 of part C, we're to calculate the weight of the 0.24 kilogram mass. So weight is equal to mass times gravitational field strength, W equals mg. 0.24 kilograms multiplied by 10 newtons per kilogram will give you 2.4 newtons. Part 2 of part C, by taking moments, calculate the weight of the meter rule. So if we take moments about the pivot and use the principle of moments, we can say that the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. So in this case, we'll have that F1 D1 is equal to F2 D2, where F1 is the weight of the meter rule and D1 is the distance to the pivot from the weight, the center of gravity, and F2 is the 0.24 kilogram mass that has a weight of 2.4 newtons, and D2 is its distance from the pivot. So W, or the weight of the meter rule, is what we're looking for. The distance will be 0.50 minus 0.18. Why 0.50? Well, because we're told that it's a uniform meter rule. If it's a meter rule, then it has a distance of 1 meter. If it's uniform, then its weight will be right at the midpoint, half of that 1 meter. So then the distance to the pivot will be 0.50 minus 0.18. And then the anti-clockwise moments, that will be 2.4 newtons times its distance of 0.18 meter. So 0.50 minus 0.18 will give you 0.32 meters. So to find W, we will transpose and divide by 0.32 meters. Meters will cancel out, we'll be left with newtons. When we calculate this, we'll get that the weight is 1.4 newtons. And then part 3, we're to calculate the magnitude of the force of the fulcrum acting on the meter rule. So we can use another principle where we say that the sum of the upward forces is equal to the sum of the downward forces. So our upward forces will just be the normal reaction force acting at the fulcrum, and our downward forces are F1 and F2 as we had labeled them previously. So that's 1.4 newtons plus 2.4 newtons, which gives us that the force of the fulcrum acting on the meter rule is 3.8 newtons. And that's question 2. Question 3. Part A. Using arrows, match each mode of heat transfer to one correct description. So conduction, we could match that with transfer without medium movement. Convection, we could match that with transfer by medium movement. And radiation, we could connect that with transfer without a medium. The question said you do only one, but I'll just show you other correct answers that are also acceptable. Conduction could also have been matched to transfer by physical contact. Convection could have also been matched to transfer through liquids and gases. And radiation, that could be matched with transfer by electromagnetic wave. Part B. Figure 7 shows a section of a solar water heater which utilizes the greenhouse or glasshouse effect in its operation. Part 1. You're to briefly describe the greenhouse/glasshouse effect. So you could say something like, the greenhouse effect is a natural process where greenhouse gases in the Earth's atmosphere trap heat, preventing it from escaping into space. This warming effect keeps the Earth's average temperature at a habitable level. The process is similar to how glass in a greenhouse traps heat. Part 2. The energy absorbed from the sun by a solar water heater is 360 kilojoules. 35% of the energy is transferred to 1.5 kilograms of water in the pipes. You are to calculate the final temperature of the water if its initial temperature is 30 degrees Celsius, using the specific capacity of water being 4,200 joules per kilogram degree Celsius for 6 marks. So first thing I would do is I would find 35% of that 360 kilojoules. Since it is kilojoules, I would multiply by 1,000 and get 360,000 joules. So 35% of that would be 126,000 joules. Then, using the formula E sub h is equals to mc delta theta, substituting the values I know, I'll have 126,000 joules is equal to 1.5 kilograms multiplied by 4,200 joules per kilogram per degree Celsius multiplied by the final temperature minus 30 degrees Celsius. So the final temperature minus 30 degrees Celsius will be 126,000 joules divided by the 1.5 kilograms and the 4,200 joules per kilogram per degree Celsius. Joules will cancel out, kilograms and per kilograms cancel out, and this will give me 20 degrees Celsius when I work it out. So when I transpose, the final temperature will be 20 degrees Celsius plus 30 degrees Celsius, which gives me a final temperature of 50 degrees Celsius. Part 3. Explain why the pipes or tubes are made from copper. Well, you could say that the pipes are made from copper because copper has a high thermal conductivity and it is very durable. Its high heat transfer capability ensures efficient absorption and transfer of solar energy. Additionally, copper is resistant to corrosion and can be easily soldered and sealed, making it reliable and long-lasting. And that is question 3. Question 4. Part A. Figure 8 shows a circuit diagram with a low voltage power supply circuit which can be used to test whether a given material is a conductor or insulator. Part 1. Describe the procedure which would be used to test whether the material is a conductor. So you could say, step 1, place the material in series in the circuit, Then close the switch, and finally observe the filament lamp. If the filament lamp turns on when the material, then the material is a conductor. Otherwise, it is an insulator. Part 2. Name one material which is an electrical conductor and one which is an insulator. So for the conductor, you could use any of the following. You could say copper, silver, gold, iron. For insulators, you could use any of the following. You could say wood, rubber, paper, plastic. Part 3. On the diagram in figure 8, mark the direction of electron flow. So, electron flow is when electrons actually flow from the negative terminal around the circuit to the positive terminal. That's the opposite of conventional current. So on the diagram, you would draw arrows that go from the negative around to the positive terminal. Part B, figure 9 shows a circuit diagram which has a combination of 4 resistors and an ammeter A. You have to calculate the reading of the ammeter when the switch is firstly open. So we have to first find the total resistance when they are in series. If the switch is open, then the resistors of 3 ohms, 6 ohms, and 1 ohm are simply in series. So the total resistance will be 3 ohms plus 6 ohms plus 1 ohm, which will give you 10 ohms. Then the current will be the voltage divided by the resistance. So 12 volts divided by 10 ohms gives you 1.2 amperes. Part 2 of Part B. Calculate the reading of the ammeter when the switch is closed. So now if the switch is closed, then the 3 ohm resistor next to the switch and the 6 ohm resistor are now in parallel. To find the resistance in parallel, we use the formula 1 over R is equals to 1 over R1 plus 1 over R2 and so on and so forth. So that resistance in parallel will be found by finding the reciprocals of the 3 ohms and the 6 ohms. So 1/3 plus 1/6 gives you 1/2. So the 3 ohm and the 6 ohm resistor together, when you find the reciprocal, gives you that those together make up a 2 ohm resistor. Now those two together act as a 2 ohm resistor and is then in series with the 3 ohm and the 1 ohm resistor. So simply adding those up gives you a total overall resistance of 6 ohms when the switch is closed. Now the current, that's going to be again voltage divided by resistance. So 12 volts divided by 6 ohms gives you a current of 2 amperes. Part C, we're to calculate the power dissipated in the 1 ohm resistor when the switch is closed. So we know the current is going to be 2 amperes when the switch is closed. The voltage, we can find 1/6 of the 12 volts, which will give you 2 volts. Why can we simply find 1/6 of the 12 volts? Well, because when the switch is closed, then the overall resistance is 6 ohms. In series, the voltage is shared in a direct proportional manner. So that means that the 3 ohm resistor will get 3 out of the 6 ohms in terms of the voltage. The 2 would get 2 out of the 6, and the 1 ohm resistor will get 1 out of the 6 of the full 12 volts. So 1/6 of 12 volts gives you 2 volts. Then the power is given by the formula P equals IV. Power is current times voltage. The current is 2 amperes, the voltage is 2 volts. That gives you 4 watts. And that is question 4. Question 5. Part A, Part 1. Define the term electric field. So you could say an electric field is the region of space where the force of an electric charge can be experienced. Part 2 of Part A. Figure 10 represents the electric field between and around 2 charged objects. You are to simply state the type of charge at object A. That would be a positive charge. How do we know it's a positive charge? You have to look at the direction of the arrows. The direction of the arrows are pointing outwards. That's how you know it is a positive charge at A. And they are going inwards towards B. That's how you know B is a negative charge. Why is it like that? Well, it's because the direction of arrows is the direction that a test positive charge would experience the force if it were placed there. So if you were to place a positive charge in between A and B, they would get repelled from A because two positive charges would repel each other, so it would be pushed away, and it would be attracted towards B because opposite charges attract. Part B. Explain how a polythene rod, when rubbed with fur, becomes negatively charged. So you could say something like, when polythene is rubbed with fur, it becomes negatively charged because electrons are transferred from the fur to the polythene. This transfer of electrons is due to the triboelectric effect, where certain materials, when rubbed together, cause electrons to jump from one material to another. The polythene gains these electrons, resulting in a net negative charge, while the fur loses electrons and becomes positively charged. Part C. A magnetic relay is used to switch on a circuit carrying a large current. Figure 11 shows an electromagnet used in a magnetic relay to operate the starter motor of a car, as you see there in the diagram. You are to explain how the magnetic relay can be used to operate the starter motor in figure 11. So you could say something like, a magnetic relay in a car's starter system acts as an electromagnetic switch, allowing a low current ignition switch to control a high current starter motor circuit. When the ignition switch is turned on, a small amount of current flows through the relay coil, creating a magnetic field that pulls the soft iron armature, closing the main circuit to the starter motor. This allows the high current required by the starter motor to flow through the metal contacts and to the starter motor, enabling it to turn the engine. When the ignition is turned off, the current to the relay coil is interrupted, the magnetic field then weakens, and the soft iron armature returns to its original position, breaking the circuit and stopping the starter motor. Part D. Figure 12 shows a wire connected to a center zero galvanometer. The wire is placed between the poles of a permanent magnet. State what is observed on the galvanometer when the wire is moved in the direction shown by the arrows. So part 1, if it's moved parallel to the magnetic field. So we would need to use Fleming's right-hand rule. So Fleming's right-hand rule, as you see there, you would place your right hand with the three fingers parallel, each perpendicular to each other, I meant to say. And so you would first place your forefinger, or your index finger as it's also called, in the direction of the magnetic field, going from north to south. Then the thumb goes in the direction of motion of the conductor, and then your middle finger or center finger is the direction of the induced current. Now, if the motion is parallel to the magnetic field, then there will be no current that is induced. The motion has to be perpendicular to the magnetic field. So if it is parallel to the magnetic field, there will be no current that is induced, hence the galvanometer needle does not move. Part 2. If the wire is moved upwards through the magnetic field, well, exactly as the diagram there shows, if the motion of the wire is upwards, then the center finger will show the direction of the induced current. So the current will flow from the background to the foreground of our diagram, and it will come around from the left hand side and approach from the left over to the right of the galvanometer. So that means that the galvanometer needle will deflect to the right. Part 3. What if the wire is moved downwards through the magnetic field? Well, then in that case you would need to flip your right hand upside down, and so in this case the middle finger will point in a direction such that the induced current flows from the foreground of the diagram to the background of the diagram, and so it is now then going in the opposite direction, coming from the right hand side of the galvanometer over to the left. So the galvanometer needle will deflect to the left. And that's question 5. Question 6, part A. A single nuclear fission reactor could produce most of the electricity requirements for many Caribbean countries. Part 1. State 2 arguments against building such a nuclear reactor in one of the larger islands of the Caribbean. So 2 arguments against building a nuclear fission reactor are, you could say, there's the issue of nuclear waste disposal or storage, and the possibility of a catastrophic accident. Or you could pick as well from this option the huge initial construction costs. Any 2 of those would work. Part 2 of Part A. Give 1 argument to support the building of such a reactor to produce the electricity required for an island. You could say 1 argument to support the building of a nuclear fission reactor to produce the electricity required for an island is a very small amount of nuclear fuel will consistently generate a very large amount of electricity. Part B. Part 1. Define the term radioisotope. So a radioisotope is an unstable form of a chemical element that releases radiation as it breaks down and becomes more stable. Part 2 of Part B. Radioisotopes have useful applications in the fields of medicine, agriculture, and industry. Choose 2 of the fields above and describe 1 useful application of radioisotopes in each. So you could say, let's go for medicine. 1 useful application of radioisotopes in medicine is in the diagnosis and treatment of thyroid cancer and hyperthyroidism using iodine 131. In agriculture, 1 useful application of radioisotopes in agriculture is labeling fertilizers to study nutrient uptake by plants. Part C. The letters P, Q, R, X, and Y represent 5 different nuclides. So as you can see there, P has an atomic number of 19 and a mass number of 40. Q, atomic number 92, mass number 235. R, atomic number 18, mass number 40. X, atomic number 92, mass number 238. Y, atomic number 19, mass number 39. We were to determine, part 1, which nuclides have identical mass numbers. So, identical mass numbers would be P and R. Both of them have 40. Part 2, how many neutrons are in the heaviest nuclide? The heaviest nuclide is the one with the biggest mass number, 238. It has 146 neutrons. How do I determine that it's 146? Well, showing my working is 238 minus 92. The mass number minus the atomic number will give me how many neutrons there are, which is 146. Part 3, which pair of nuclides are isotopes? So you could say P and Y are isotopes. Both of them have the same atomic number but different mass numbers, right? Isotopes are 2 atoms of the same element that have different amounts of neutrons. So P and Y are the same element with the same atomic number, 19, but they have different amount of neutrons, in other words, different mass numbers, 40 and 39. You could have also used Q and X, because they have the same atomic number, again, but different mass numbers. Part D. In an experiment to determine the half-life of a radioactive isotope, the initial count rate of 16,000 counts per minute was recorded. After 100 seconds, the new count rate was 1,000 counts per minute. Use the information given to calculate the half-life of the isotope for 4 marks. So, half-life is how long it takes for the activity or count rate to decrease by half. So we take the 16,000 divided by 2, that will give you 8,000. 8,000 divided by 2 gives you 4,000. 4,000 divided by 2 gives you 2,000. And 2,000 divided by 2 gives you 1,000. So that is 4 half-lives. Now if that took 100 seconds, then the value of the half-life will be 100 seconds divided by 4, which gives you 25 seconds. And that's question 6. Please hit that like button, subscribe, and share with others. Good luck on your exam this year.